Guillaume.
Yeah, thanks for the invitation. So let's have a look. So there's probably way too much content, although Nashi did a really good introduction this morning, so you all know everything now. So we may be able to go a bit faster. I've called some stuff refresher, but it's a refresher if you've done the AGDA course based on PLFA. Otherwise, it's new content. Don't hesitate to tell me to slow down. The important thing is that there's one or two interesting messages that are going through, right? You'll see the goals first, and then it's more technical details. So here it's the opportunity to like give you usual tips and tricks of the trade. And if we don't get to the end, we don't get to the end. It's not a big deal. Here. Okay. So let's start with the goals. Well, we can have two different kind of goals. We can do generic programming. For instance, we can have type classes that describe the sort of usual capabilities various objects can have. And then you can generically program against these interfaces and instantiate these generic programs so that they work with the different objects all in the same way. Or we can do meta programming. For instance, you have a circuit description language. So your language is sort of high level, and eventually you want to get to actual circuits, or rather descriptions of circuits. We're not going to manufacture anything. And the idea here is that we would like, the common idea is that we would like both of these to be done in a type-safe manner. So we want at compile time to be assured that the programs we write make sense. And then when we run them, there will be no errors whatsoever. And ideally, we want them to be at no abstraction cost. So I'm writing these generic programs. They're very general. But then when I instantiate them, I want specialization to happen so that there's no overhead from the fact that I did this very generic description. And it's the same for the circuit description language. I want to generate the circuits and then be able to go directly into production. I don't want to have any like functional terms laying around anymore. And the difference then between generic programming and meta programming is that for generic programming, the idea is you're using the language itself to describe some constructs that are useful. And then the specialization sort of goes from the language back to itself. But you've added, you didn't need to write as much code because you had this very generic programs you could just instantiate. Whereas in the meta programming aspect, ideally you'd like to program in a richer programming language. So the idea is that you have access to a lot of power. You can write really short programs that do amazing things that generate a ton of code. But then the target is a smaller language, a simpler one. So for instance, having like this very expressive description language so that you don't need to write a mux for 2 signals, 3 signals, 4 signals, etc. You just write a generic one. But then eventually you go to circuits where you actually need different ones for the different arities. And the one solution, so this is fairly recent work, it's derived from homotopy type theory, but actually can apply to functional languages, is to have what we call a 2-level type theory. And it's a single language that's equipped with, so 2 levels, as the name suggests, a compile time one and a runtime. And actually, so we are only talking about 2 levels today, but you could have arbitrarily many levels. Because you could have an extremely rich programming language at the top, and then slowly go down the abstraction layers all the way to your circuits, for instance. So you have your 2 levels, but then you want also a compile time function. Well, no, okay. You can write your compile time functions that generate complex, potentially runtime patterns, but you want them to go away. And you have that because in your framework, you're ensuring that your 2 levels are mediated by a partial evaluation algorithm, which will take the things that contain both compile time and runtime information, and then execute all of the compile time computations so that you're only left with the runtime ones. So with the polymorphism, the type classes example, for instance, so partial evaluation would grab your type class dictionaries, put them in all the right places, and then try to do some inlining so that they're not around anymore, etc. For the circuit description language, well, you might be using very abstract higher order functions to describe your circuits. You also want these to go away in the process and then be left with circuits. So I have this small table here telling you what the different languages are. For instance, so if you have your type classes, you could have, let's say, idealized Haskell, where you have no overhead whatsoever when you use type classes. And that would be because you would have this mediating partial evaluation operation that would take you from Haskell with type classes to Haskell with no type classes. Of course, in reality, it's not quite true. And in the circuit description, so I've picked just the simply typed lambda calculus because this is what we're going to see in the rest of the talk. And then for runtime, you want circuits, and you don't want functions anymore. You don't want application, lambdas, and so on. OK, so let's look. We're still looking at the goals. This is the simplest example you could cook. We're starting with a small term. So there's a lot of noise because all of this is Agda code. It's fully formalized, type checked. You know it's correct. But basically, the idea here is that this is a notation for the type of circuits with one input and two outputs. And then there's some noise here in the middle, whatever. And this is implemented just as a bunch of wires. So telling you that the first input comes from the first output comes from the first input, and the second output comes from the first input. So this is duplicating the original signal. We can write this thing, and then we can write something that's a bit weird if we're talking about circuits. So if we look at the meaning here on the right-hand side, we're actually writing a functional that takes like any circuit you might like and returns one where you've only have one input, you duplicate it, you feed it to both inputs of the circuit you took as an argument, and then you pipe the outputs out. So on the left-hand side here, what we have is, again, there's a lot of noise, but intuitively, we're taking a circuit with two inputs, one output, and we're turning it into a circuit with one input, one output. The up arrows and so on are explaining that the types are basically navigating between these two levels. So the types of circuits that we have here are runtime, but because we're manipulating them in a sort of abstract manner, we're saying, well, I'm talking about the code for a circuit. I don't really know what the circuit is. I'm not going to inspect it. I'm just going to plug it somewhere. And if we look at this definition here, it's using nameless syntax, but we can see what the general structure is. We first take the circuit that is passed as an argument using a lambda abstraction. And then we take the sequential composition of the duplication circuit we saw above, which will give you the signal into two copies of the original signal, and then sequentially composed with just the name of the argument we got, so the variable referring to the argument we got, which is exactly this pattern in a sense. And the magic of the two-level type theory then comes next. Well, we can already write these terms that are talking about the different phases and that are mixing both very like hardware heavy and also functional heavy concepts. But now what we will be getting from the two-level type theory is this notion of partial evaluation, which will get rid of all of the high-level concepts, such as lambda abstraction, variables, application, and so on, and only give you circuits. So famously, you can get NOT by taking the diagonal of an AND gate. And here on the right-hand side, we can see that this is a checked comment. I don't show you the proof, which is just REFL. But basically, it's saying that if we take this definition of NOT as the application of the diagonal function to the NAND gate, then it actually evaluates to the sequential composition of duplication and NAND. So it means that with the small language that we're going to introduce, hopefully be able to see all of it. You will be able to write circuits using functional principles, but then you still have a guarantee that you're only producing circuits. And this guarantee is given to you by the type system. So I'm not showing you all of the types. The ones we can see are already disgusting enough. But the type of the result of evaluation guarantees that there are no lambdas, there are no applications, there are no variables left. The only thing you are left with are sequential composition, wiring, and basic gates, and so on. And parallel composition, I suppose, also. Okay, but how can we build such a thing? So if we're in ACTA, well, we can, if you were to use any other functional language, you could just write your parser, your interpreter, and so on. And then you would do a proof on paper guaranteeing that your partial evaluation is actually removing everything. If you're using a proof assistant like ACTA, you can actually have very precise types that allow you to precisely explain what is getting erased during partial evaluation. And so in particular, you will be able to see in the types that these things are gone. But to do that, we need to first represent syntax. So it's a common issue. We'll just have a very simple language to begin with a single level, no circuits, no nothing. We just have a base type, alpha, and then we have a function type between two arbitrary types. So I'm using backticks here for the name to mean that they are constructors, they are not semantic things. So that distinguishes between the actual type of functions and the type of the constructor for the type of functions. And then we can have contexts. So as Nashi was saying, they don't show up when you're writing your programs, but internally we need to keep track of them. Because when you go under binder, there's a new free variable in scope. You need to be able to refer to it. So you need to keep track of what is available and what is not. So these contexts, I'm using notation, which should remind you of the inference rules we typically see. They can be either empty, or you have an existing context and you extend it with a most local variable. And here, I'm not giving a name or anything because names are really tricky to get right. And so it's much easier in a mechanized setting to just use a nameless syntax. On that note, so here at the top, we have the S combinator. I don't know if you remember what it is, but it's basically taking a first function, a second function, and then an argument, and then computing this gx of fx thing. So it's fairly self-contained, but there's still like an interesting binding pattern and binding pattern. And below here, you have a graphical representation of a nameless version of it. So each binder is not carrying a name anymore. It's only, well, here we have colors to help us, but it doesn't actually really matter. So we have a lambda, we have a second lambda, we have a third lambda corresponding to lambda x. And then we have some application nodes. At the top here, we have g of x, and here at the bottom, f of x. And every variable now is just a number telling you how many binders you need to cross to find the one that introduced the variable. Okay, so we can now formalize this in ACTA by giving this definition. And the idea is that basically you're taking your rules that you have at the bottom here. If x is in scope, then x is in scope. And if x is in scope, then x is in scope with an extra y that's there, and we don't really care about it. And this is the two constructors corresponding to it. So remember that we're talking about these nested, like right nested contexts, right? You always extend it with the most local variable to the right, and we're only talking about these extensions. So if the most local variable to the right is already of type A, I can have a variable of type A that lives there. It's this one. And otherwise, if I have any extension whatsoever, and I know that I have a variable in the rest of the context, I can just lift it to be a variable in the most local in the context with a new local extension. And if you squint hard enough, you might notice that here, so we're defining the type family var indexed by types and context. Here it only shows up in the return type. So there's nothing to the left. So it's a bit like a base case. And here it shows up both on the right-hand side and also on the left of an arrow. So it's a bit like a successor in a sense, right? It's like, go fetch it further. So this is, in a sense, the well-typed version of the Brown indices we were seeing earlier. We are only counting how many steps we need to go, how many binders we need to skip until we reach the one that was responsible for introducing this variable. So once we have variables, we can start formalizing terms. So terms are also indexed by both their type and their context. And we will have one constructor per rule, basically, in your inference system. So on the right, again, we have the typing rule. So it's saying if X is a variable in A of type A, if somewhere in the context, then X is also a valid term of type A. And how do you translate this? Well, you add a new constructor to your family, saying that if you can prove that you have a variable of type A, then you get a term of type A. And here I'm using combinators to make the context implicit, just like the context is implicit in all my inference rules, but it's a purely technical thing, a cosmetic thing. So once we have variables, we can also have applications. And because we are in the business of ensuring that all the programs we write make sense, we will force our, and so we're pushing our types onto the terms. Our application only makes sense if the function actually is a function type. And if the term that we take as an argument has a type corresponding to the domain of the function. And then overall, this constructor, which will be an application node in our parse tree, essentially, will have a type corresponding to the codomain of the function. We can see that all of the invariants that are described by the typing rules on the right-hand side are enforced in the introduction rules for the family we're describing. And finally, our minimal lambda calculus is not ready with that lambda abstraction. So it's exactly the rule you'd expect. So to implement a function of type A to B, you push a new variable of type A in the context, and then you just build the body of type B. And this is what this gadget is doing, but it doesn't really matter what the exact notation is. OK, we can put all of these together, and suddenly we have a scoped and typed syntax for small programs. And you can, for instance, write the identity function from A to A. It's simply a lambda abstraction. And then we want to return the variable we just bound. So we use the var constructor. We need to prove that there's a variable of type A somewhere in the context. But luckily for us, it's the most local one. So we can just use the here constructor and get access to that variable. OK. So once we have our syntax, it's not yet two-level. It's not yet talking about circuits and so on. But we already have in mind the idea that maybe we want to evaluate the terms we're writing, because eventually our goal is to have two levels and partially evaluate one of them. So it would be nice to know how to do partial evaluation in the first place. So what we would like to have is an eval function that's turning terms into values, and then maybe we can turn the values back into terms or something once we're done. And the problem is that we have these potentially open terms, right? There are free variables floating around. So we can't just turn any term into a value. We also need an interpretation of the variables. So this is saying that if only I could make sense of the variables in gamma in terms of values living in delta, then I can take a term in gamma to a value in delta. And this will be done in a type respecting way. You don't want your evaluation to just randomly change the tree. And in order to build that, we'll need a bit of machinery. So the first thing we need is this notion of order preserving embeddings. Then it might seem scary. It's very simple. It's telling you that you can take all the variables in gamma and you can push them into a bigger context delta in a way that is preserving the order. So if x comes before y, then in gamma, it should also come before y in delta. But this can be defined inductively, which is really powerful because then you can inspect these proofs claiming that one context is smaller than the other to do some computations with them. Crucially, these form a preorder, which means that any context is related to itself. That's a fairly sensible thing to do if we are thinking of it in terms of embedding the variables of one into the other. And then if you have two such proofs, you can compose them to get a proof that the smallest of the context embeds into the biggest one, just by going via gamma in between. And yeah, I think that's the main things here. And then we have a very important concept, which is so we can have a lot of families indexed by context, right? But only some of them are well behaved with respect to contexts getting bigger. And we just define this concept by saying that they can be weakened. And what does it mean to be able to weaken something? Well, if you have a proof that gamma embeds into delta and you have a value in the current world, then you can get a value in a future world, so the world delta. And so if you're paying attention in Natchi's lecture, this is a bit like the Kripke structure he was talking about. And then it shouldn't be any surprise that it shows up when you're building models of your lambda calculus, because if I go back to my example, oh no, maybe I have it here actually. Did I? Oh, I thought I had put it here. If I go back to my example term, so here I'm taking G, F, X, and building this body. And if you think of how this is going to execute, if you apply this function to an argument G, well, you might have a value for G already, but it's going to need to travel under F and under the binder for F and under the binder for X before it is used here in the middle. So your notion of value, it needs to be well behaved enough that you can actually open the binders, enter a bigger context, and your value is still valid in a sense. So this is why we are defining this notion of ordering on the contexts, because this is the generalization of what it means to just be extended by a single binder. It's extended by arbitrarily many binders. And why we define this notion of weakening. If your values can be weakened, then you have a chance of actually building an interpreter, because when you encounter a lambda, you will be able to go under it and keep working in the extended context. Okay, so that's in particular, there's this very important proof that gamma embeds into gamma extended with a single variable. And I'm not showing you the proofs because they're not very interesting, but we can already prove that some families, existing families, are well behaved. So the variables in particular are well behaved, and the terms also. The variable case is actually pretty interesting because if you look at the definition of weaken, right, it's saying if you have a proof that gamma is less than delta, then any variable in gamma can be transformed by an algorithm into a variable in delta. So this was the informal specification I gave you of what it means for a context to be smaller than another one. And now we see that there's actually an action associated to that informal specification that can actually do the translation between the variables in one context into the ones in the other. Okay, so what do we want? We want this thing. Oh yeah, okay, that was coming a bit too late. The weakening. Okay, so now we've seen what we want. We just build the machinery to describe what it means to go under a binder and so on. And we can finally put the pieces together and just build the model that will allow us to partially evaluate the functions in the small language that we have. So we're introducing this box modality. So Nashi had a very general box modality that is working for an arbitrary relation between different worlds and so on. Here, our worlds are contexts, and our relation is just going into a bigger context. And so what this box modality is saying is that for any proof that for any delta, and any proof that delta is bigger than gamma, I can give you a value of P at delta. So it's really this idea of closure under all possible future worlds. And this has really good properties, which are also common properties in model logic. There's no need to look at the implementations, just look at the types. If I know that I have box P, then I can get P. And this is just saying that if I'm happy to have a value at any future extension of the current context, in particular, having no extension at all, or the trivial extension, which is empty, is a valid strategy. And duplicate is telling us that if we can take our current P to any world in the future, well, we can do it in 2 steps instead of just 1 step. And this is what the transitivity was showing earlier, right? You go from gamma to delta, and then from delta to theta. It's the same as going straight to theta. And then we can give our interpretation of what it means to be a function from one type to the other by saying, well, first of all, if you have a value right now, I can give you a value right now. But also this promise is valid at every single future world. So it's this idea that the function, the value associated to a function is valid not only in the current environments, but could also be transported under a bunch of binders and used in a bigger context, in an extended context. And then there's a bit of syntax here. This is basically saying that we have a semantic notion of variable binding, which is taking a proof that we are in a bigger context, a value for our arguments, and then we can build the body inside, just to make the function that's coming up a bit nicer. Okay, and why do we call this like a Kripke function space? Well, because it does behave like a function space, right? This is exactly the same argument we had with extract. If something is valid at any future extension, in particular, it's valid right now. So if you have a Kripke function space between P and Q, in particular, you can get a function from P to Q. But you're getting it at the current world. If you want to use it later, it's too late. You forced your function to be living in the current world, and now it cannot be transported anymore. So morally, you want to keep it in Kripke form for as long as possible, and then just at the use site, you turn it into an actual function by formally applying it as a value to some kind of arguments. And by construction of this thing, it will be you will be able to push it on the binder. So this is what the full quantification at the beginning here is doing. It's guaranteeing that you can always go further and further. Okay. So now that we have everything, we can actually build the model that in which we will be able to evaluate our functions. So the values for the base type will just be terms. You could insist that they are in normal forms, but here we're just saying they're standard terms. And then the values for functions, there will be these semantic functions that you're actually able to embed into a bigger context if you need to. And so now the notion of value that we have itself can be pushed under binders, because if you remember earlier, I didn't show you the proof, but I told you that terms could be weakened. They're just pure syntax, so you just manipulate the syntax. And then the Kripke function spaces are just can be weakened just by construction, which means that all of these values can actually be transported no matter what type they live at under binders, which then gets us to the definition of environments. So the eval function was taking an environment for the variables in scope and then evaluating a term to a value. And the secret in the environment is just that it's a mapping from variables to values. And because these values can be pushed on the binders, so can environments, entire environments. And here it's a gadget. So if you try to parse the type, it's telling you that if I have a given environment and I get a value, I can build a bigger environment. And finally, we get to build our evaluation function. So the environment is from gamma to delta. Then we have a term from gamma, and we get a value in delta. And we do this by, of course, inspecting the term that we want to evaluate. Or I could have been cute and called this var or something, and then we would go from syntactic var to semantic var, and then from syntactic application to semantic application, and from syntactic lambda to semantic lambda. But you can see that we've just built enough structure in the model that we can do a direct interpretation of our constructors as their semantic counterpart. And everything type checks and terminates, and we're happy. Should I do the? I mean, we can see a little bit of it. Right. So what about the two-level type theory? Well, it will be mostly the same. There will just be something slightly different. So here I'm showing you an example. I'm applying the what I call the dynamic identity, which is the identity that will compute at runtime, to an application of the static identity, so one that's present at compile time but should go away, to the dynamic identity. So all very boring so far, but a nice thing to see is that it evaluates, partially evaluates to an application of the dynamic identity to the dynamic identity. So the static one computed away, but the stuff that was purely dynamic is still around after partial evaluation. There's a bit of noise. Don't look at the 2/3 at the top of the slide. Just look at the bottom. You still have your base types, and you still have your function types. The crucial thing here is that both the domain and the codomain of the function need to be living at the same level. You can't do cross-level things. The only cross-level thing that exists is this up arrow thing that takes a dynamic type, so a type for the generated code, and give you a static type. And morally, you can read this as a program that will eventually compute something of that type at runtime, or a representation of a program which at runtime will behave like this dynamic type. And then you have your syntax of terms. The standard terms are the same. There's just more noise because I've thrown in more noise. But then you have two interesting operations which are really doing all the work here. There's this quote operation, which if you have a term for a dynamic value, you can see it as a term for code for that dynamic value. So it becomes a static term, which will basically just be plugged in for that value, right? You're saying, I just want to insert this something somewhere, so I'll treat it as code instead of an existing value. And then if you have code for a program that will compute an A, if you have static code for a program that will compute an A, you can get a dynamic program of type A. And this is where the partial evaluation will happen, right? Your code may be involving arbitrarily complex static information, but it will all be gone once you've done the partial evaluation, and you will just get a dynamic code. And this is the static and the dynamic identity functions. Only the types are different. The syntax doesn't actually need to carry all of this noise around. What do we want? Well, we want the same evaluation function, essentially. And then from it, we'll derive a staging operation, which takes us from terms for dynamic values with terms with none of the static crap inside anymore. And the punchline maybe a bit more time, is the model construction. So if you look at the bottom here, the model construction is essentially the same. Static values of the ground type. Well, I don't have any constructor for them, so I could just say it's any term of that type. But realistically, you're not gonna be able to manufacture any. So I just said the empty type. And then static functions will be Kripke function space between static arguments and static results. And then the nice thing is that you now have this extra like code for programs of type A. And the static meaning of this will be a dynamic value of type A. And what are dynamic values? Well, dynamic values are terms because we have not evaluated them. It's for the runtime to actually process them and run them and evaluate them. And we can write an evaluation function that looks a lot like the previous one. So now it's a bit tricky because the model construction is set up just the right way, which means that the meaning of quotes, and this is called splice, seems a bit silly. We're just returning the value immediately. It's not actually doing anything interesting, but that's because everything interesting is happening in the other cases, because the partial evaluation is kicking in the other cases. So I think I have so the application, now in the static case, it actually computes with Kripke function spaces and it passes the arguments and evaluates the body and so on. But if you have a dynamic application node, it stays dynamic. This is what we saw in the example, right? Only the static identity function was computed away. Similarly, for the lambda, there's a bit of noise, but you can see that in the dynamic case, we emit a lambda constructor. And in the static case, we use the semantic lambda. So here it computes, here it doesn't. Then we can implement staging as just evaluation. OK, do we have like 5 minutes? OK, that's good, actually. So far, we've only seen like a very basic language, and then we've added a second layer, but the second layer was exactly the same. So it might be interesting. Well, we don't have polymorphism, so we can't really do the generic programming I was talking about, but you can see how that would work. But then we can, with exactly the same machinery, have much more exciting, like heterogeneous languages, where the two stages are widely different. So the one I like to do is the one with circuits. So the types are the same as before, but now I have this type of I inputs, O outputs circuits. And I'm throwing in extra constructors. I have an AND gate, which is 2 to 1. I can do parallel composition of circuits. I can do sequential compositions. Everything is created by construction in terms of the arities. I'm sure I'm not losing any wires on the way. And then I can have the wiring. OK, I didn't give you the type of the wiring gadgets, but you can see that with this mix operator, you can write all sorts of wiring patterns that you can then use in your circuits. So in particular, we can recover the diagonal functional that we described at the very beginning, not, and then you just unroll your like digital logic thing. You can define and, or, and then anything you like. You can even write funny circuits. So this thing is taking a function from a Boolean to a 1 input, 1 output circuit, and it's giving you a 2 input, 1 output circuit whose behavior is essentially the same. So the new input you're getting serves as the argument to the function, right? So this kind of gadget actually allows you to write function-looking things in your source program, but eventually generate circuits. But instead of manually doing like the parallel composition, the muxes and so on, you just encode this pattern once and for all, and then you can just reuse it. And you can try to follow along, and this should correspond to the various parts in the diagram, with the original Boolean doing the controlling on whether we taking the first or the second inputs. Okay, so what next? Well, we've seen, oh, I didn't show you the partial evaluation function, but basically it removes all the functional things. So then you can use your normal like PL theory to actually prove the soundness and completeness of the language you describe using logical relations, etc. The program I showed you, so it's a limitation of the system. Here we have static input and output values, but nothing prevents you from actually defining once and for all a tabulation function going from IO to suc IO. Except for having a type system that's expressive enough that you can actually write that pump. There's a question of whether we can automatically lift an existing language to a two-level type theory so that you don't need to manually redo all of the work. And then when we're looking at the evaluation function, we're seeing that the interpretation of quote and splice was very boring. We're just passing the values around. And so here, there is a wiggle room to actually have more interesting primitives in your language. So a generalization of the tabulation we saw earlier would be to take an arbitrary function between bit vectors and give you a circuit that corresponds to the tabulation of that function. And this, even if your language, like the one I have here, is not expressive enough to actually pattern match on I and on O, you can push that power into the model construction and have a generic interpretation of the tab operation that actually gives you this power. And going the other way, so this would be the quote. Is it the quote or the? I always get confused. But going the other way, if you have a circuit, then you can actually run it on a given bit vector to get the bit vector of outputs. So it's really the idea of using static values, compiling away static values to get dynamic stuff, and using dynamic circuits at runtime. Yeah, I think that's it for today.
Writing this by hand seems really, really arduous. Is there anything you do to make this more enjoyable? I suppose. I mean, I mean, what I mean is, you know, you encounter this all the time, which is you come up with some nice improvement over Verilog, over other existing ways of doing things in industry, and then you show it to someone in industry, and they say, "Well, I'll never do that, right? Because I'm right." Yeah, that entire bridge, is it just something that's completely orthogonal, in which case ignore me, or is it something you've thought a little bit about?
Not really, no. So it's all in Agda because we have really tight control over all of the types and everything. I don't know how you would hook that up to an existing language.
Yeah, that's fair.
Hello, thanks for the talk. I think you briefly mentioned about generic programming.
Yeah.
So like in C++, we have like spine, right? Substitution failure. How would you handle this? Like, because I know a lot of people want to have like a generic type that handles, say, int and float. Let's use a simple example and decide which one to substitute with. Can this handle that? Like, just like going a bit beyond the talk.
Yeah, so looking at the circuits, right, we're programming against an interface, basically, telling us what the constructs of the circuits are, but it's still uninterpreted. So in your language, you could have a layer that has a notion of numerals, for instance, And then you would write numeral generic codes, and then in a type-directed manner, it would tell you which of the interpretation to substitute into the generated term.
Right. So I guess that's similar to like concept and constraints in that sense. Like
I'm not familiar with
right,
that. Yeah.
okay.
Yeah, another example that we have in dependent types is very common to give a description of a universe of data types, for instance. So you're saying my data types are closed under sums, products, fixed points, etc. But then you can write a generic fold over them or various operations to manipulate these data types. But the problem is that the codes remain at runtime. So what you're actually running is the generic function which acts as an interpreter over the code rather than the specialized version. But with this technique, you can make sure that the description is only present on the top layer, on the static layer. And then in the dynamic case, you will only have specialized functions.
So, hello. Thanks for the talk. It looks to me like there is a lot of boilerplate about converting back and forth from static and dynamic. Can this boilerplate be automated away using another language, maybe? But
right. So here, all the terms are intrinsically typed. So you have your constructors, you need to write them and so on. But there's a similar like noisiness to representing bidirectional languages using an intrinsic representation. But the user wouldn't be writing this. The user would be writing just a program without all the annotations everywhere. And then you would have an elaboration pass that takes your original program and turns it into the one with all of the invariants built in. And of course, if it cannot, because one of the invariants is broken, then you get an error message. But yeah, in your compiler pipeline, this would be the core, but this would not be what users are writing. So in theory, you could get the quotes and the splices to be inserted using just type-directed casting, basically. It might be dangerous because as soon as these kind of things are inserted automatically, if you make a mistake, but the computer is able to recover somehow by inserting it somewhere else, you might not get the program you meant to write. So I would be wary of this, like especially when you're talking about partial evaluation and performance and so on.
Yeah, the issue in that case would only be performance, right?
Yeah.
Because even if everything is dynamic, then it's fine. It would still compile fine. Thank you.
Hello.
Hello.
Hi, Guillaume. How are you?
Right.
Thank you for your talk. I don't know whether it's related to the first question, but I was actually wondering if the input is sort of written in this De Bruijn language, that could be quite difficult or maybe no fun. So I wondered whether you've been thinking. I mean, one could use Kripke again in a way and use this what's called second-order generalized algebraic theories or higher-order abstract syntax. Have you thought about doing this to make it more sort of fun to do this?
Well, that's a good point. You could have like a domain that you don't actually use, and then verify from it. Yeah, why not? I guess the concern is that you could write exotic terms in your domain, because if your host language is expressive enough, you can actually inspect the arguments you're getting and then write things that are not actually valid terms.